Okay, folks, if you're here for the first session of the dairy ventilation talk, we're going to get started. We've got a great program here today, something we've never done at the conference, and that is to have kind of a part one and part two on a topic, and that is ventilation and heat stress abatement. And I want to just tell folks again, I told you about, remind you about the evaluation forms. There's one for each session you have you fill out. This topic actually came from your feedback last year. One of the highest rated topics was ventilation. So we said, well, let's do talk on ventilation. And then we said, well, let's have Dan McFarland come. And he was pleased to do that. And I want to introduce a great colleague in Extension, but also one of our native sons, Dan McFarland, graduated with some of you guys here in Delhi a few years ago. And I can tell you, when I came into Extension, I mean, it's always been the case, Dan McFarland is one of the top people in ag engineering in the country. And we're thrilled that he said yes and would come speak to us, even offered to do webinars and stuff if we want in the future. So happy to have Dan. He started here in Delhi, went to SUNY Catskill, went to work for about 10 years for clay manufacturing, and then went back and got his degrees from Iowa State and ag engineering, and has worked since 1989 for Penn State Cooperative Extension as an ag engineer. They've got a great ag engineering program. And Dan is one of these people in my circles in Extension that we really look up to. We're glad that we have him as a resource. Dan, welcome home.
Okay, yeah, it's great to be here, actually.
And you've got the slide advancer. There's a thing here. And
do I need a mic, or I've got a big enough mic?
Just speak loud. You can either that mic or you can carry this one.
Okay. Well, some people know I have a big mouth, so I probably can get along without a mic. Boy, it really is great to be back here. I grew up here, spent 20 years here, and it's always home. Whenever I come back and get nestled into these foothills, it just always feels good. And so I appreciate the opportunity. I appreciate Paul and Marianne inviting me back to give you some information. I appreciate the committees, wanting me to speak and on these topics, because they're ones that I've worked with and really like to talk about. But I really want to thank you for coming. I know you're taking time away from your business today to come and listen to me and other speakers, and being an educator and knowing how hard it is to get people out to meetings like this, I really appreciate the opportunity to speak to you. But they asked me to talk about ventilation today, and one thing about ventilation, I've tried to study and work with ventilation for about 40 years. And early on in my career, it became very apparent that there's some basic principles that we need to follow in designing and operating ventilation systems, but it is as much art as it is science. And so applying these principles to your individual situation is usually very unique. And so we're going to cover some very basic things. We're not going to get into a lot of detail on what you might do to your facility, but maybe to get you thinking how you might improve your facilities and why you're doing it in main thing. It's not a new topic. W.D. Horde in 1885 wrote that what does a cow live on? She lives on food, drink, and air. And you take away the air and she will die the quickest, won't she? There's an old saying that says a cow will survive 3 weeks without food, 3 days without drink, and 3 minutes without air. I haven't found any research on that topic, and I haven't found any farmer willing to let me test that, but I'm going to take it for granted that you need that fresh air. And so it's not a new topic, and we're still working on it. And you think of the cow in 1885 compared to the cow today, and that cow needs more fresh air than she did. And so it's something that really, really is important. Ventilation systems, I mean, the most important thing to remember is that it brings life-sustaining oxygen into the building. And it also controls moisture levels, dust and pollutant levels, as well as temperature levels in that building. Simply, it's bringing in fresh air. That fresh air comes in and mixes, picks up moisture, odors, gases, dust, pollutants, and then that moist, stale air is exhausted from the building in some way. So ventilation systems affect not only air temperature in the building, but the uniformity throughout the entire animal space. And that's very important as we talk about inlet systems and how to design that type of thing is we want that uniform air quality throughout the entire animal space. Moisture level, cows produce a lot of moisture. On a hot day, they may produce up to 8 gallons of moisture just through respiration a day. That doesn't include what comes out the back end and evaporates from the alleys and that type of thing. So we've got to control moisture in there and condensation to surface. Surprise to you, you know, cows produce gases and odors. And so we want to limit those concentrations as well as the airborne dust and disease organisms that may entrap themselves in the moisture as well as the dust and be inhaled by the cows in the barn. Also, the airspeed across the animals. You know, what's the difference between a breeze and a draft? And it's typically the temperature. It's the same airspeed, but it's at some different temperature. We want to control drafts in certain types of the year. We want to create breezes in other types of the year. And not so much anymore, it seems, except to some calf buildings, maybe unvented heaters. We want to get the carbon dioxide produced out of the barn. If we look at air quality and what is air, it's mostly nitrogen, about 21% oxygen, and then the remainder is some argon and very little level of CO2. But those CO2 levels, that carbon dioxide levels, can increase very quickly if the air exchange is not provided. And livestock alter the air composition within the buildings. And so breathing uses oxygen, but it also creates carbon dioxide. And if the oxygen levels get less than 16%, it starts to get dangerous. And if it's less, or causes discomfort. And then under 10%, it can be very dangerous and fatal. And so we want to take that. Again, the gases and odors and also moisture, we want to control those levels as well. Some of the gases we're concerned about, certainly is ammonia. It's created by fresh manure and the decomposition of that manure. But it's one that'll cause problems in the upper respiratory tract, as well as an eye irritant. In the hog industry, we can often see pretty elevated ammonia levels significantly simply because the eyes start tearing and you'll see these streaks coming down the pig's faces because of the dust in the air that's absorbed into that moisture. And we know that there's usually an ammonia problem in that. Prolonged experiences to that or exposure to it is going to increase the opportunity for respiratory disease. Carbon dioxide is another one. It's created by respiration. It displaces oxygen. And so if we don't have that good air exchange, that life-sustaining oxygen coming in there, it can cause a problem and could become fatal. Hydrogen sulfide usually isn't a problem in most barns. The levels are usually pretty good, but when you agitate manure, that's when you release very high levels of it. So if you're scraping manure or you're agitating manure, you're going to increase those hydrogen sulfide. That's the gas that smells like rotten eggs, then it dulls your senses, and then it kills you. So you need to be very careful when you're dealing with hydrogen sulfide. And of course, methane is also produced by respiration of the cows, but it's mostly from manure decomposition. It's very highly flammable. It can be explosive, usually not a problem in most livestock facilities, except in contained manure storages where that gas can build up. And then carbon monoxide, if you're any internal combustion engine or heaters, things like that, are going to create CO2. It can be dangerous and fatal at high levels. So those are the things we're kind of control as far as the odors and gases. When it comes to moisture, looking at air temperature here, different air temperatures, moisture production, we look on this side and look at turn that into gallons per hour, and perhaps up to 8 gallons of moisture per day just through respiration, these cows. And we got to get that moisture out of the building to make it more comfortable there. So that moisture control, we take this cold air outside, okay? Its volume is, because it's cold, it's fairly low. It contains a pretty high relative humidity typically. We bring that into the barn and heat it up. When you heat a gas, it expands. We've got the same amount of moisture in that. So now it has the opportunity to pick up more moisture in that building. Okay, and then that's exhausted out of the building, and you take that moist, stale air out of the building. So the goals are to provide fresh air exchange, control these levels of moisture, gases, pollutants in the animal space, uniformly distribute it throughout the entire space, protect from weather extremes, both hot and cold. We're going to talk about hot this afternoon. And then we want to mix that incoming fresh air in the animal space without creating drafts, at least during cold weather. The goal of a ventilation system is to have the air quality inside the building similar to what it is outside with respect to moisture, gases, odors, and pollutants. Notice that temperature isn't necessarily there, especially in loose housing or freestall housing. There's 3 ventilation systems. It's cold, which would be winter. We're experiencing it right now. A warm season in the summer, and then there's these transition periods, which you're going to experience this weekend. Okay, we're going to go from very cold up to maybe 60 degrees this weekend up here. So we need a ventilation system that can adjust to these seasons and these conditions as well. The ventilation system alternatives are either mechanical, there's negative, positive, and neutral systems, which we'll talk about very briefly, natural ventilation systems, or a combination of both. We have a naturally ventilated building that uses mechanical ventilation in hot weather, or with the case of Calves, we may have a naturally ventilated building that uses mechanical ventilation in the winter to provide that air exchange. Negative pressure ventilation system, we have a series of fans as well as inlets. What these exhaust fans do is develop a lower pressure in the building, a slightly lower pressure inside the building. So high pressure outside the building wants to come in through these planned inlets. So we look at this from above. We have the fan that takes that out. We get this uniform distribution throughout the animal space. This is a very minute pressure difference. Static pressure is the difference between inside and outside. We use a U-tube manometer to measure that. We put one end of the tube outside, one end of the tube inside in a U shape, and then that high pressure outside will push the water level down, and the difference in those levels is what we call the difference in the static pressure. With most ventilation systems that we're talking about, we're looking at 1/100th of an inch of H2, and so that's why we have to use an inclined manometer, as we see in the upper right, in order to measure that, because we're looking at 1/100th of an inch in that way. Positive pressure systems, just the other way around. We've got fans with a duct or a tube of some site, bringing fresh air into the building. And then we have outlets on the outside of the building, so we're increasing the pressure inside that building, so that now that high pressure wants to get outside of the building. So basically overhead, that's what that would look like. Neutral pressure system uses a combination of both, in that we have a very similar pressure within the building. It might be equal or slightly higher or slightly lower. We're using fan and duct to bring air into the building and distribute it uniformly. And then we're using fans to provide a more predictable, exhaust fans to provide a more predictable exchange. Natural ventilation is driven by the wind. Okay, so in this case, where the curtain on the prevailing wind side is closed, the wind blows against it, creating a high pressure on that side of the building. Air goes up the roof. That because that air is going further and faster, it creates a low pressure, and so we get a draw at the ridge. But on the opposite side of the building, we're creating kind of a suction, and so it can draw air out of the building as well. So we can create an air exchange that way. So this would be more typical during cold weather. What we'd see is trying to block those prevailing winds, open up the curtain on the other side of the building to allow that air to exhaust out of the building. During summertime, we open things up. We want to create just this pavilion effect for the cows, open things up as much as possible. And so the bulk of the ventilation is by the wind blowing across the dimension of the building. The ridge is still working, but its contribution to the total ventilation is negligible compared to what's happening through the sidewalls. Natural ventilation is also heat driven. Warm air rises. Cows create this heat. And you'll see it on mornings like this, where it might be very still, and you've got the animal heat in the building because there's a bigger temperature difference between cow level and the outside of the building that drives this air up. We'll see this plume of moisture just coming right out of the ridge in that case. It works very well when you have that big temperature difference, but wind really is the primary driver of natural ventilation. Negative pressure ventilation systems require a system of multiple fans, typically. Well, I'm going to say always. And then fresh air inlets as well as controls. The recommended rates, typically the cold weather rate, we call it the continuous weather rate. It's the continuous rate. It is the exchange you need no matter what the temperature is. It's providing oxygen in the building and doing something to remove moisture as well. And so temperature is not in there. If you need supplemental heat in some facilities, you may need to add it during these periods of time. But it's what you should never shut things down. because that CO2 concentration can really build up if you just close everything up tight. These animals are breathing, they don't stop breathing. Well, they might if you keep it up long enough, but they don't stop breathing if the ventilation system isn't working. So mild weather rate, and that's typically what you'll find in most systems, is they're working somewhere between the mild and the warm weather rate. So around 200 to 300 cubic feet per minute, typically per cow, is what most systems will run on in actual practice. And then the hot weather or warm weather rate, 500, and hot weather rate is the minimum of 1,000 CFM per cow. And there's some arguments looking at, just the way cows are today, that we might look at 1,500 CFM. Per cow. Most tunnel ventilation systems are going to be in the range of 2,000 to 3,000 CFM per cow in that rate. So what we need is a system that really needs to provide an infinite range of ventilation rates between 50 and 1,000 CFM per cow. And so that's going to require multiple fans, inlets that adjust to the number of fans that are operating to maintain that static pressure we need for that uniform distribution, as well as accurate controls in order to accommodate that or to achieve that. And we have controls available now that can do this and sensors that can do this. It's just tremendous what the improvements have been over the last 40 years in the control portion of ventilation systems. In selecting those fans, you want to, a fan is not a fan. There are good ventilation fans and there are bad ventilation fans. And I think you need to look at those quality ones that provide good efficiency as well as they're rated. And rated is usually, there's a couple of labs out there. One is the Air Movement and Control Association located in Chicago. It's the label on the left. And then Best Labs, which is at the University of Illinois. And what they do, if they're independent testing labs for companies that choose to accept their rating. They have to send a fan to the lab tests it, it gives the rating, sends it back with the agreement that they can use this test data in their literature. And so you really need to look at those. Best Labs actually has a website that you can go up and look at the company and the fan and see what theirs is in getting that. Because you want to evaluate these at 1/10 to an 1/8 inch static pressure. Now we're only running it at 400 to 600 static pressure, so why do you rate them that way? Well, fans get dirty, belts slip, the wind blows against them, and you want to be able to have that performance to achieve that 400 to 600 static pressure, inches of static pressure, even though these fans are operating under those conditions. You want to consider energy efficiency. So high efficiency motors will save you money in the long run as far as operation of that particular system. As I mentioned, fan is not a fan. Here's brand X and brand Z. I actually pulled this off the Best Labs data. They're both 36-inch belt drive fans, but when we look at their capacities in the range that we would look at, they're very different. The one on the left, 9,600 CFM versus 7,000 CFM. And so you want to consider that as you're buying a fan. Simply look at the rating, make sure it's rated, and make sure it's the fan that you need. But you need to maintain these fans as well. Again, they get dirty. There's this environment that these animals are creating. There's a lot of dust and so on involved. It can build up on the fans. And especially on smaller fans, it can affect their performance up to 40%. So it's a good idea to keep them well maintained, the belts tight, replace belts when needed, and you need to keep those shutters and guards in place for safety. Circulation fans are not designed to exchange air. They're egg beaters. Basically, you've got an egg beater in a bowl, you're mixing things up. That's all they do is just blend air, mix it up, provide some air movement around the cows. They're not meant to exchange air. And so you need to keep that in mind in buying fans as well. When we look at inlets, we want that uniform distribution and mixing throughout the entire animal space. Again, in colder weather, not causing a draft. And so that air comes shooting into the building. We want it coming in about 700 to 1,000 feet per minute. At that velocity, it kind of sticks to the ceiling. And as it gets further and further away, it begins to fall, slow down and fall and mix with the air that's in the building, okay? And then moves through the building and through to the exhaust. There are continuous inlets and intermittent inlets. Continuous inlets work very well at these higher rates, but at the minimum rate, this 50 CFM per cow that we typically design for, it's very difficult in ag construction to maintain that tight opening throughout the entire space. And so we often consider intermittent inlets, which are typically half the length, okay, but twice the weight, and in that we now have an opening that will be easier to maintain in most of these systems. Maximum distance between a fan and an inlet is 75 feet. Typically at these lower rates, what happens is that, again, it's coming in the inlet fresh, but it's picking up moisture, odors, gases, dust, pollutants. The closer it gets to the fan, the worse quality of the air is. When I started looking into ventilation design, we put inlets on one side and we put fans on the other. And guess what? The best cows were always on the inlet side because the worst quality air was down towards fan, especially during these colder conditions. When we started putting inlets all the way around the barn and cows got fresh air all there, all of a sudden we had high producing cows all over the barn. And so we learned that by experience, which we do most things. Typically, you want to provide 2 square feet of opening for every 1,000 CFM of fan capacity. Okay? So a 10,000 CFM fan, we need what? 20 square feet of opening to do that. Now that opening is going to adjust depending on needed, but anyway, we want to close and seal all unplanned inlets, such as this. This is what we call short circuiting. Okay, it's not doing anything. Okay, so we want to avoid that. There are a number of different types of inlets. Ones are manually adjusted, and I've got some producers that have built 100-cow barns. They put in fans, they put in tunnel ventilation, and they're going to use windows for the inlet during cold weather. Now, I know you have better things to do during your day than to adjust those windows to accommodate the fans that are running, okay? So slots, you can do that. There are baffles that you can adjust manually. You can adjust all the baffles with a single winch, but you need a gauge there to help you maintain that static pressure that you desire to get that good mixing, or you get short circuiting, or you starve the fans. If you just have one setting and the fans are going on and off, you're either going to starve the fans or you're going to get short circuiting. So we want some automatically adjusting ones. Here's some that are self-adjusting. The automatic baffle on the left has a sensor that senses static pressure in the building, and it'll open and close the inlets throughout the building depending on that. These weighted ones simply just open and close as needed as the fans delay. They're very simple. They work very well. You need to be spaced properly, that type of thing, but keep in mind. The opening to those inlets needs to be twice as big as what the inlet accomplishes. And that comes in through either the attic space or directly from the outside. So for this example, a 6-inch maximum baffle opening needs a 12-inch opening to it, unobstructed, so that you get that good air to that. In that Eave Inlet, you don't want to use a residential soffit, which have these pinholes to ventilate the attic space, because we've got cows that are breathing in there and they need more air. So we use that 3/4-inch mesh in order to keep the birds out, but provide good fresh air into the building space. Again, as I mentioned, controls need to adjust those inlets and fans according to the conditions inside and outside the building as needed, especially during these transition periods of warm to cold in that. They need to be convenient at a convenient height so you can observe them and know what they're doing, but you don't want to put them on an outside wall because they'll get a false reading typically, if it's a thermostat, or you don't want to put them over cows. Again, the heat coming off the cows is going to give a false reading in that particular cow. A lot of these new controls available send sensors out, and they're just little sensors that hang in the building that can measure that. You can mount the components on the wall there because they're sensing out near the building. So usually in a tie stall barn, that would be over the service alley, the center alley, between the cows. Freestall barn would be mounted throughout the barns too if you are mechanically in. I just wanted to go through a couple of design examples using a 60-cow dairy in this case. If I'm going to completely mechanically ventilate this building with sidewall fans and then have adjustable inlets in here, this is what we're looking at. As far as 60 cows, we're going to need 3,000 CFM, cubic feet per minute for those cows. That's the continuous. No matter what is happening outside as far as temperature, we want to be able to provide that amount of air exchange in order to get oxygen into this building. Mild weather rate jumps up to, in this case, to 210, I figured. So a little over 12,000 cubic feet per minute. And then warm weather through 30,000. This hot weather rate at 1,000. And keep in mind, we might add another 30,000 to that in some cases, but up to 60,000 cubic feet per minute. You cannot do that with one fan. Okay, the fan law says, I mean, the RPM determines the amount of volume or capacity you're getting out of that fan. But the problem is we're working with motors that don't have a consistent power throughout that range. And so at these lower rates, it's not going to deliver as much as it does during the upper rates. And so we want to have multiple fans in this case. And so for this particular one, I selected 2 banks of fans. Each has 4 fans of different sizes. 3,500 CFM fan, that would be roughly an 18-inch fan. A 6,500 CFM fan would be a very good 24 or 26-inch fan. And then the 10,000 CFM fans would be about 36-inch fans, good quality 36-inch fans. Some of those are 2-speed and some are single-speed, so that they provide that range that we're looking for between that 50 and 1,000 CFM per cow, depending on what's needed in that case. I also added some circulation fans over the cows. We'll talk about heat stress later and why that's needed, but basically we want to put air movement over the cows in hot weather too. So some circulation fans, well, there's the continuous inlets. In this case, I needed continuous inlets to get enough inlet for the fans that are being provided in the sidewall in that case. But I also added some circulation fans over the cows to provide that air movement in between the cows when this air exchange is occurring. But I also looked at what people seem to be more interested in now is looking at ventilating for this cold to warm weather rate, and then looking for hot weather, they're looking at a tunnel ventilation system, which is going to really work out very nice. So in this case, it's 2 banks of 3 fans each. And so we got about 20,000 CFM per bank, so a total of 40,000 CFM. So we can take up to the warm rate really well. But then we can also now use these intermittent inlets, which are going to help during cold weather in maintaining the opening that we need compared to the continuous inlet. But now we look at tunnel ventilation, where we're opening up one end of the building as a fresh air inlet and using fans at the other end in order to achieve that. Just going through that tunnel ventilation design, it's very easy. That's why I can do it. Is that we've got a building that's 38 feet wide, 9 foot high. That gives us, we take the height of the building and the width of the building. That gives us square feet. That's the cross section of that building. Now we want to move that wall of air down the length of the building at some speed. And typically we look at least 3.5 miles an hour, which is 308 feet per minute, or 5 miles an hour, which is 440 feet per minute. Okay. And so square feet times feet per minute is cubic feet per minute, and that's how you buy fans. And so for the 3.5 mile an hour, we got a little over 105,000 cubic feet per minute requirement. We go looking for some fans. I found some 51-inch fans, 27,000 CFM at that 10th inch static pressure. We got 108,000. Always round up with CFM. You'll appreciate it. So 108,000 CFM in that case. If we want to go to 5 mile an hour breeze, which cows really do like, we can bump up. We need about 158,000 CFM. We bump up. We find those. We use 6 fans now. Get 162,000 CFM in that barn. Now we got to determine the inlet required. So for that first group, those 4 27,000 CFM fans, we divide or we multiply 108,000 CFM times 2 square feet per 1,000 CFM. We need 216 square feet of opening, which is a 6-foot opening across that width of that barn. Okay, that gives you an idea. If we want to do 5 miles an hour, in that case, then it's 324 feet. That's a 9-foot opening across the end of the barn. There's a little bit of play in that. I don't want to make that an iron rule, but that's about what the inlets you need in that case. And so we get that rapid air exchange in the barn. We get a cooling breeze, and it really, tunnel ventilation systems do work very, very well and hot. And I think the primary benefit is the rapid air exchange you get to get rid of the moisture that's being produced. And it keeps things dry in that barn, also providing that air movement over the cows. But it is not intended for use in cooler weather. I know it happens. It happens in Pennsylvania. Maybe it doesn't happen in New York, but I know it happens. The problem is we look at that cold weather rate, which was what, 3,000 CFM? We look at the mild weather rate, which is around 12,000 CFM. We've got one fan doing 27,000 CFM fan, and all it's going to be doing is going turning on and off, on and off. And so you get this temperature difference within the building because it's moving too much air through the building. You won't be satisfied with it uniformly. Great for summer, not intended for cold weather use. We still want to use that sidewall fan and inlets, and then you'll get that almost seamless air quality throughout the year as we move through especially these transition times. But what about existing structures? Okay, that's great for new structures, Dan. But what do you do for an existing structure that they really didn't think about ventilation when they built the barn? Well, believe it or not, there's a few barns in Pennsylvania that have this problem. And it's kept me busy for the last 30 years. So some of these extension ones. So as far as the fans and figuring out the capacity, it's the same as a new barn. Same with the inlets. The calculations and the inlets you might use are going to be the same. It's just getting the fresh air to those inlets that is often the challenge. And so we look at one way to do it is bring directly from outside. We can open up the sidewall, put a wind hood over that, and bring it right into the inlet. We can do that. There are some wind effects that'll happen, especially in these weighted inlets that happen, but it works and it can be done. Also, we can, especially in cold weather, why not bring this air in through the mow area, mow space, that's not affected by wind pressures. And there is ways to duct that air down through, where the rafters are. We can bring that air down through that opening. We can build something there. Or if you've got open space in that floor, we can build some kind of a device to bring that air down through there. And that works very well. Yes, it takes time. It takes some creativity and it takes some investment, but it's definitely worth it, again, to bring that fresh air into the barn. When it comes to renovating for tunnel ventilation, my gosh, we get really creative in this cases. Okay, we can put fans at cow level. We can put them upstairs. We can put them in the sidewalls. Fans are easy. It's getting the inlet, enough inlet that's usually the concern. And so we have to be real creative with inlets as well. Is how do we get that 2 square feet per 1,000 CFM in that barn so we can satisfy the fan capacity of that barn. And so we get real creative in that way. And again, it might take some time, it might take some thought, it might take some inconvenience, but certainly we can do that. As far as natural ventilation, there are some things that have to be thinking because we're dependent on wind speed and direction in order to create this air exchange. And so the orientation of that building to the wind is very important. The separation distance between buildings, the sidewall height and opening, as well as the ridge opening and eave overhang, all these things have to work together in order to get the exchange that you want in that building. As far as building exposure, we'd like it to be nice and open upwind, okay? If there is some obstruction upwind, it's going to challenge the airflow to that building or the wind's effect on that building. And it can disturb airflow. Any obstruction upstream can disturb airflow 5 to 10 times the height of that obstruction, okay? Usually this is going to be the biggest concern during hot weather when we're looking for that maximum air exchange. Okay, we want that building, I mean, as an engineer, I want that building perpendicular to the wind, to the predominant prevailing wind. We know the wind doesn't always come from the same direction though, right? But if it does, the wind sees more of the building sidewall, so it can pick up air and pull it across the building, okay? It also moves, is more effective to the ridge. If the wind is looking at the ridge of the building along the entire length, there's a more even draw out of that ridge. If we turn that building 45 degrees, it's seeing about half of it, or 7/10 of it. So it's not drawing as much. If it's parallel, it's screwing things up. And so we want to take that into account. But really, wind direction up to about 45 degrees to the long axis of the building, the length of the building, is usually acceptable. The area I'm in is probably very similar to here, is that we have westerly winds. And typically in the winter, they'll be from the northwest, and in the summer, they'll be from the southwest. And so we look at this kind of thing. We've got an open front building. We will always want to put that open front away from the prevailing wind. So somewhere between south and east in most cases, we want to put the southeast is a good orientation. So we look at that, and we look at a north-south orientation, probably for these westerly winds, gives us the best wind exposure and exchange simply because it's blown across the short dimension of the building, okay? But as far as the sun, which we're concerned about during hot weather, is it's rising in the east. I think it still does up here. Rises in the east, and we get sunlight intrusion in the east side of the building, and it sets in the west, getting sunlight intrusion into the west side of the building, which if we've got stalls there, cows don't want to use them, or they tend to avoid direct sunlight if they can in hot weather. And so that's a concern. So really a lot of the industry, much to my chagrin in many cases, because I think it's may not be the best option for people if they would consider, is the east-west orientation, which doesn't necessarily favor wind. It's okay because those northwest and southwest winds, but a direct west wind, it's going along the length of the building. There's some eddies that occur and the ridge doesn't work as well and that type of thing, but we can live with that. But it does give the best shade line across the building during hot weather. And so that's why people go. There is a compromise, northeast, southwest, which gives you kind of a compromise of both. It gives you better, I think, better air exchange and acceptable sunlight intrusion compared to the other two. But what I do know is the cheapest way to level the site is how it's going to be laid out. That's just what I found out in experience. Building separation, 50 is the minimum from any obstruction, and these would be lower obstructions like some light trees or corn. I have one farm, I didn't put the slide in, but he planted corn about 10 feet from his prevailing wind side, and it grew very well this year and really affected the ventilation of the building. But I'd really like to get rid of that 50 feet because it's really not enough. 75 feet or more is preferred. Some people figure 2.5 times the building height that might be upwind from it. So if it's 30 feet, we're looking at somewhere 75 feet or more in that case. And then there's this equation, wind shadow. I often kid that in order to keep my engineering degree, I have to show a formula with every presentation. And this is the wind shadow formula, which you take this distance is dependent on the height of the upwind building as well as the length of the upwind building. So in this case, we've got a machinery shed, which would usually be, solid sides, all that type of thing, providing quite an obstruction. We take all that into account. This is about 21 feet high and 40 feet wide. We really, according to that equation, which is really pretty good, we need about 83 feet between the building. So it's not interfering with the wind, especially in hot weather. But if we're putting another ventilation or another dairy barn upwind, then we're looking in the range of 256 feet, which might be hard to find in Delaware County. It's hard to find in southern Pennsylvania. So anyway, so often they get jammed up pretty tight, and it does affect especially summer ventilation. Sidewall height in a naturally ventilated building, at least loose housing, this would be bedded pack or freestall, would be at least 12 feet. Bedded pack probably 16 feet. But 14 to 16 is preferred, and it really depends on the building width. We get increased wind exposure, but we also get more volume in the building. And if the solution to pollution is dilution, the more volume of air we have in the building, the more opportunity to pick up moisture, odors, gases, dust, pollutants. It's a good thing as far as the cows are concerned. Sidewall opening, our guideline in new design is 11 square feet of sidewall opening on the prevailing wind side per cow, okay, or per stall, depending on what you want to do. That's the minimum. If we look at the 3-row freestall, for example, with a 14-foot high sidewall, the actual opening is somewhere in the range of 12 feet because we've got, a support for the trusses, and then we've got some concrete coming up. So it takes so 12 feet at the most along that length. We get a little over 20 square feet, almost 21 square feet of opening per stall in that particular one. But if we double that building, we have a drive-through building, 6-row. Now we have 6-row, we have 14-foot high sidewall. Now we're at 10. We're a little below where we want to be. So maybe we want to consider a higher sidewall in that particular barn if we're going to ventilate it this way during hot weather. We want it adjustable so that we can open up as much as possible during warm weather, especially at cow level, because that's where we want those cooling breezes to come. So as much as 100% of that opening, we just want to make this building a pavilion for these cows, provide shade, provide as much fresh air as possible to get in and out of that building. But during the colder weather, we want to block those winds, especially at cow level, at least on the prevailing wind side. If the wind is blowing from the northwest, we can open the southeast, that south side, to allow that lower pressure on the other side of the building to draw that moisture and pollutants out of the building. end walls. It took me several years to figure out the end walls or sidewalls too, but we can open them up as well. And that can be done with curtains or doors, but open up as much as possible, provide that pavilion effect. As far as roof slope, typically, gable roofs, we look at 412 providing good volume within the building. It's a reasonable cost as far as snow loading, things like that. Does add more volume to the building and really provides some height to that building so that when that air blows up or that wind blows up that roof, it's creating that low pressure at the ridge and drawing moisture out of the building. Continuous ridge opening, probably up here, 2 inches per 10 feet of building width with a minimum of 12 inches is a good guideline. Down in the banana belt of Pennsylvania where I live, we look at 3 inches simply because we're just a little bit more temperate down there than you are up there. But you get a 100-foot wide building, we're looking at 20 to 30 inches or more of opening in that building. There are a number of different ridge options that can be used. The open ridge usually is the best, but there's some weather protection, some weather exposure that needs to be addressed. Some of these other ones, like here down, the overshot ridge is very popular in Pennsylvania, the builders, because it can it can protect the top connection of that truss a lot better. And then the one on the other side is overshot with the upstand, which basically is an overshot, and then there's an upstand here, so the air comes up and out. So the wind blowing from the west or so on is going up over this side. When the big storms come, at least down in Pennsylvania, they come from the southeast, and that sets up that ridge. And so we get very little weather intrusion into that building with that particular design. Primarily, freestall barns are cold barns. They're non-insulated. They're referred to as cold barns. And so when it gets cold, they get cold too. Okay, and that to keep in mind. In cold weather, we're looking to block wind and provide protection from, we want to keep these cows dry as well. So we want to keep precipitation off them in that case. In warm weather, provide that shade, that pavilion-like system I said, and provide breezes at animal level. In cold weather, in order to avoid moisture problems, typically the temperature inside the building will be no more than 5 to 10 degrees warmer than it is outside in the shade. I'm sorry. Manure is probably going to freeze some time of year. It needs to be handled. During warm weather, about the best we can do is get 1 to 3 degrees inside the building warmer than it is outside in the shade, because we've got all these furnaces in there that are working. And it's not going to be. So we need some additional heat stress abatement, which we'll talk about a little bit later. In my opinion, and you can take it as however you want, is I really favor air quality over manure consistency. Because I think that moisture is the biggest problem. It can cause respiratory problems and it can cause production problems as a result. And so we want to do that. I'm sorry for the inconvenience, but it's somewhere. However, if you keep it warm and wet enough in the barn, the cows will probably get sick, and that'll favor manure consistency, be a lot looser at that point probably. So maybe if that's what you want, we go with that. As far as that control, and here again, that transition becomes the real problem, is that, cold days, if it's going to get cold and stay cold, you can set those curtains and leave them alone. But typically you're going into a barn and you're concentrating on cows, not what the curtains are. And so, it's getting really hot, and okay, we'll go adjust the curtains that way, or the other way around, close them up. So there's hand witches to do that. I think it's better to get some kind of automatic control, and the most common is probably just temperature. We set that at some temperature, and the curtains open and close according to that temperature. The best ones, though, respond to temperature and wind speed and direction. And there are a couple of these controllers out there, which I think are just fantastic for naturally ventilated barns. Because what they do, they use this control, and basically they put sensors throughout the barn. And there's sensors in the barn, and there's sensors just outside the barn. And every 5 minutes, it goes around to these sensors, and it says, okay, the temperature outside is this, the temperature inside is this, we want it to be this, and so we'll adjust the curtain up or down in order to try to accomplish that. And it provides this nice uniform, and it's interesting to watch, especially I've done some time lapse here in colder weather. And it's surprising how open these curtains are in cold weather, simply because of the wind and temperature requirements within that building. And so that is something I really think is a good investment if you're building a system that is using curtains on that. So the advantages of natural ventilation is that wind speed and direction determine the air exchange. Okay, it's natural, you know, and everything's got to be natural now. It's simple, it's relatively low cost and relatively low cost of operation, and it's quiet in most cases, okay, in that way. However, there are some concerns with natural ventilation, is that wind speed and direction determine the air exchange. And in periods of little or low airflow, then it reduces the air exchange within that barn. Improper sidewall opening compared to what the conditions are is typically a problem. And then circulation fans are required in the summer, especially at these periods of little, low, or no airflow in order to blend air within the building. And the wider the building becomes, the more of a concern it gets, okay? And it's really a challenge. As the building gets wider, that sidewall has to get higher if you want to provide the right air exchange within that building. My cohort, John Tyson, he's based in Mifflin County, a little more towards the center of the state, did his master's thesis on ventilation and heat stress abatement. And he came up with this natural ventilation factor, which I think is pretty good in evaluating buildings. Is he looked at these risk factors, the ventilation opening, orientation to prevailing winds, and exposure to winds as three things, and then rated them best, medium, or poor, depending on the you know, what score they got. And he said that with good natural ventilation, that number is 4 or less. If natural ventilation is compromised, it's going to be 5 to 7. And if you need, it's greatly compromised if it's, you know, 8 or more. And so I think it's a good guideline. It works pretty good. I'll just run you through an example here, which you might, okay, all of a sudden we've got sidewall openings that are 7 to 11 square feet per cow, which is not bad. That's still pretty good. But the shelter is parallel to prevailing winds, so we're not getting the good air exchange we'd have if it was oriented a little better. And there's some scattered trees and small buildings upwind. This gets a score of 7. And so what do you do there? This is usually going to compromise hot weather ventilation, warm and hot weather ventilation, more than it is cold weather ventilation. So maybe it's something where you go and look at some mechanical means during warm weather to achieve, you know, the kind of conditions that you'd like for these cows. One way to do that is tunnel ventilation, and there's a lot of tunnel ventilated freestall barns in the United States, and they work pretty well. You got fans at one end, a lot of them, and then inlet at the other. Because we're doing the same thing with this. We're taking the width, we're taking the interior volume of this, or cross section of this barn, that's square feet. Now we want to move it at 4 to 6 miles an hour. So that's going to increase that. And so we're going to have a boatload of fans at the other end. And so you need space to put the fans there too, especially in existing situations, but it can work. There are some issues with tunnel ventilated though. The big advantage is that rapid, predictable air exchange. So you're not dependent on the wind in this case. You're going to get an air exchange if it's designed properly to control those. And we usually want that in less than a minute. We want to move air from the inlet to the outlet in less than a minute in those cases. Cooling breezes, 4 to 6 miles an hour. Unfortunately, in a freestall situation, air doesn't have a conscience. And so it's not looking for a cow to cool. It's looking for a way to get to the fan, which is usually a cow alley, a feed delivery alley, or something like that. And so you need to keep that in mind. There is an effect, okay, if we've got air coming in from one end and the wind is blowing at some angle to that, it's going to create a dead spot unless we've got the inlet adjusted a little bit tighter so it straightens things out. So you need to put that into the thing. It's non-uniform in the resting areas, again, because it's going around the cows. There are some design features we can do to improve that. And also you may need circulation fans to do that. And then if you got stalls along the outside, so these cows' noses are along the outside wall, air doesn't want to flow there either. But that's the end they breathe at. And so you'd like to get some air there. So what we often do in that case is we open that lower sidewall 4 to 6 inches, so that now they're getting air rushing into their noses and improve that comfort, and it works out really well. However, that's inlet, so that's inlet that we need to add capacity to, so to add more fans in that case. Another way to do that is to add building width, is to put an alley beyond that stall, so that now there's space for the air to flow in front of their noses. So that's something you can do. Problem 2, we're closing things up. We're closing the ridge, we're closing the eaves, and we're closing the sidewalls. And so it's going to get dark in that barn. And so artificial lighting is typically required, even during the summer, in order for people to do their work. just shortly, I want to mention natural ventilation is an option in tie stall shelters as well. And there's some up along the St. Lawrence Seaway, so I have a feeling they could work in Delaware County as well. But we're trying to control temperature a little bit more in these buildings, okay? Not as big volume in these buildings compared to the freestalls and that type of thing. We want to have some kind of ridge ventilation that we can control, and then sidewall curtains. And so that uniform, you know, that automatic control of curtains, again, is really important in order to maintain temperature. The big thing to remember in tie stall barns with natural ventilation is you don't let the cows out on a day like this, because the furnace just got turned off. And that building's going to cool down very quickly, and it's going to take a little while to heat back up in that case. So we don't want to freeze water bowls. We want to control temperature within that building. But it is a great system for tunnel ventilation, because now we can use natural currents and all those types of things up until it gets really hot. Then we can close the curtains, close the ridge, close the eaves, and provide that tunnel ventilation. And then if that tunnel ventilation fails, we can open the sidewalls up very quickly. Because within 5 minutes, a tunnel ventilation system that fails usually can start to get really dangerous as far as cow health and productivity. And so we want the opportunity to provide some type of emergency system with a tunnel ventilation. I'm a little more concerned with that because a number of the tunnel ventilation systems I work with are non-electric. And so they're either belt drive with LP engines, 27 to 34 horsepower, belt drive to the fans, or hydraulic systems, which run on diesel engines. And so if they fail, you know, what's going to happen? These folks like to go away on Sunday. And so what they'll often do is turn those systems off, open the building up as much as possible in order to avoid that risk in that case. So a hand winch, and this happens to be one of those in that non-electric system. So if the hydraulic system goes off, the catch on that curtain, there's a little pneumatic cylinder there that fails and the curtain falls and provides that safety net in that case. So what about calves? Just very quickly, same idea for all of these things we talked about as far as mechanical, natural ventilation. But typically, we're looking at an animal that is more vulnerable to respiratory disease, so more sensitive to that moisture in the air. So we want to keep that moisture level good. Lower immunity than her mother or aunts. And then limited thermal comfort zone. We're looking at a limited range compared to what a mature cow is. And they don't produce much heat. That rumen's not working, and at least not as active as a mature cow maybe. And so they don't produce the heat, and they're very sensitive to draft. They're less tolerant than older animals to draft. And so they need fresh air. The ventilation systems or the seasons are going to be the same, but the cold to transition are the real challenge for this group of animals. And so we want to do that. I mentioned that comfort zone. Newborn calves, 58 degrees to 78 degrees. That's their thermal comfort zone. Within a month, that spreads out to 32 to 73 in that case. But newborn calves, we got to look at it that way. So in colder weather, especially in naturally ventilated systems that we're not providing additional heat to, they're going to need bedding so they can nest. They're going to need calories so they can do their best to warm themselves up, and also perhaps jackets at this point to help retain any heat that they can produce. So we look at a per gaff method. We're looking at 15 CFM per head, 50 for the mild weather rate, and 100 CFM, quite different than a mature cow. So we take that, the number of calves times that gives us CFM. That's pretty easy to figure out. But probably more accepted, especially in the naturally ventilated ones, is we look at an air change per hour method. And so cold weather, continuous rate, it's really 4 to 6 air changes per hour. Basically, we're exchanging the volume in that building 4 to 6. So we're looking at what, every 10 to 15 minutes. We're exchanging air at that low rate. Mild weather rate, 10 to 15. And these are the ones that so we take the building volume times the air changes per hour, divide by 60, and that gives us the CFM required. See, a lot of this is simple. That's why I can do it. But I really want to concentrate on this cold weather, because this seems to be where the problem is in most calf barns, is they're not providing these exchange rate, at least uniformly throughout the space. And so what we can use to do that is a positive pressure system. Okay, we're taking fresh air in through a fan, through a duct, whether it's a polytube or a rigid duct, and it's uniformly distributing its air throughout the animal space. We can also use the neutral pressure system, which in a lot of existing systems, say you're renovating that tie stall barn that you moved out of some time ago into that freestall barn. It took you 2 years to figure out why you moved out of this barn. And so now you want to put little animals in. Okay? So what you need, it's going to be more difficult to provide that pressure system as efficiently as it should be. So now put an exhaust fan in that matches that capacity so that you get a more predictable air exchange in that building. 4 to 6 air changes per hour provides the minimum rate uniformly. And then we don't want to create a draft though, because the air coming out of this tube or out of this duct is coming out at 1,000, 1,200 feet per minute. We want it to slow down by the time it gets to the calf so it's not causing a draft. And a draft sometimes is thought about as being 60 feet per minute. I think it's probably a little more than that, but 60 feet per minute is kind of what we learned with hogs, but hogs don't have the hair coat that a calf does. And so anyway, that's for another day. But I really like to design these systems. I think you can't get too much fresh air. And as long as it's not creating a draft, why don't we just provide more fresh air? That's how hutches work. So why don't we do that? And so 10 to 15 air changes per hour is what I recommend to the producers, especially in my area. It really doesn't add that much more to the cost of the system, and it provides a bit more air exchange uniformly throughout the workout. This is just an example of a 2-row calf barn with pressure tubes overhead. Again, the hole size and position on this tube are designed so that when it gets down to 4 feet, we're below that draft level. But it's directing fresh air down to the calf in her space, okay? It uses fresh air, not recirculated air. There's nothing you want to recirculate in these barns. You want to provide fresh air to displace that moist, stale air in the building. So here's an example up in the upper left is that 2-row calf barn with a row of tubes over each row of calf, directing that air down through. This is when the curtains are more closed. There's a ridge opening to help exhaust the air. They also use the sidewalls are controlled automatically, depending on wind speed and direction in this case. In that case, or group calf housing. And group calf housing is a tremendous option that creates some unique consequences as well. And so we need to take, and ventilation being one of those things. Can also be added again to some tie saw barns that, in this case, they moved to a new freestall system with a parlor. This barn was vacant, so let's use it again. They made some good changes as far as the pens and things like that, really put some money into it. And then we put rigid ducts in there. And typically we had to put rigid ducts in there because we needed more fan capacity. So I needed more square footage than a tube would give it. A tube would have had to be really big. If we can get it into a rectangle, we can control the height. You can see here, the holes are in the side. They also have an exhaust fans in the barn. They help exhaust it about the same rate. Naturally, I just want to introduce you to that topic because really each design is unique to the system that you have, okay? These positive pressure systems operate at full speed. They're designed so that the exit speed throughout these holes is similar throughout the entire length. If you start to reduce the fan capacity, it's not going to be uniform throughout the entire length. And so they're going to operate at full speed. You really need to select someone, whether it's a trusted, it doesn't have to be an engineer, but someone who is very qualified in ventilation design in order to introduce that system to you and use the specific components that are true. Typically, if I make out a recommendation, in my letters, since I can't specify brands, I can say you need a fan of this capacity at this static pressure, okay? And you go find that fan. Now, if you ask me, I can give you 3 manufacturers, but I just can't recommend one in that case. But use, if they say 16-inch fan, say, gee, what is that capacity of that 16-inch fan? I need to know that more than the diameter because that capacity, all is dependent on that. So here we've come to the end where we started. And Hord said it again. He said, we're coming to rapidly understand we've got to furnish pure air to our cows. And again, the cow in 1885 is different than the cow in 2020. And so we need to keep that into account and maybe even provide a little bit more. Or as Bob Graves, who's one of my mentors and good ag engineer at Penn State's retired now, says, if it smells like a barn, you need better ventilation. And that's about as simple as it gets. So thank you very much for your time. I'm open for questions. I usually, when I'm presenting, I don't eat a lot of lunch. So if you don't feel like you're disturbing me at lunch, if you want to come talk to me, and I'm going to be here a little bit after my second presentation. But again, thanks committee for having me, and hope you might have learned something today. Thank you very much.